After 2 years on hiatus, the famous Hadron Collider has been switched back on, as I said before. Thank God for it too. Scientists are waiting for the first new data to begin flowing from the underground particle smasher, paving the way to a new era in physics, possibly. So the big question is, what is this new era? Nanotech scientist Michelle Dickinson is here to tell us. Michelle, good morning.
Good morning.
Now, okay, first up, I love this kind of stuff.
Good, it's exciting.
Well, it's really, really interesting.
It's like the biggest car crash ever that you can control.
The fastest car crash.
It's amazing. It's the most energy we can do in a man-made thing. We're at speeds of almost the speed of light. We're at temperatures below deep outer space. It's awesome.
Okay, that's the upside. The downside is no one can see any of this happening.
Which is even better, right? Because it makes it almost magical.
If you want to see the biggest car crash in the world, you want to see it. Well, it's happening in a tube under the ground.
You can see a representation of it through the graphics and through the mass spec images that you get. Right. But it's like nanotechnology, right? People love nanotech. You can't see it, but it's still cool.
No, but also here's the other thing. This is why it's not like it, because nanotechnology is actually there, whereas the Hadron Collider is trying to find things that may actually never have existed.
But they're still there. So it's measuring things like particles and the mass of particles. It's working out the theory of relativity, whether E equals mc squared actually can exist for different supersymmetry particles. It's awesome.
It's a really, really cool machine.
Yes.
Which is trying to look at things which are invisible.
It's 27 kilometers of machine, so it's a ring in which you accelerate protons so fast, and then you head-on crash them
against
together.
each other.
How awesome is that?
How do you like, you put a lot of protons in it, do you? Or just one? Because the graphic is like there's two, one going one way, one going the other.
So you do two beams, and then you work out exactly where they're going to collide, and where they're going to collide, you have these detectors. They've got different detectors to detect different things, like the mass, like what's going on. And when you crash them together, you break down these protons into their subparticle parts. And so you see what flies off, and you work out whether or not it's real. That's how the Higgs boson was found in the last experiment.
Absolutely.
And we got to solidify the theory that we'd thought for a long time, that there is such a thing as the Higgs or the God particle, the Higgs boson particle, that holds the rest of the particles together and gives things matter. So now we're going to go look for dark matter.
Of course. Well, it's the logical thing to do.
Right.
So you've got these two beams. So if you're the unlucky proton leading the way, you know, because if I was there, I'd say, no, you go first, guys. I'll come up the back. So you've got these two. How do they get them to hit exactly? Because they're particles, they're tiny, laser beam, tiny, and they go kilometres under the ground at an extraordinary speed and hit each other square on. How do they do that?
Right, but it's all controlled in a tube, right? So it's in a big ring tube, so you know exactly where they're going to hit. We get 800 million collisions per second. So when we're talking about how many we're hitting a lot. There's heaps of data. Of that, only about 1,000 of those collisions per second are useful data that then we extract. It's a massive, big data problem. If you look at the capacity that the supercomputers need to have for this, it's processing, it's being done around the world. It's incorporating scientists who don't talk to each other, scientists from Iran, from Pakistan, from India, who are all working together on one big worldwide project. I think it's great. Science is overcoming the politics of the system.
I mostly don't understand what you're saying. Mostly. So, like the supercomputers, they only have to be super because there is so much information coming so quickly, am I right?
And it would take decades to process it if they weren't supercomputers, because we need the processing power not only just to save the data, but be able to interpret it. And to do that, we take the data, we copy it, and then we send it around the world for scientists to interpret.
Okay, so with the Hadron Collider, when it first came up, it was hugely successful. I mean, obviously, there were some teething problems. Off the grid for a couple of years while they modify it, and now it's just faster. It's exactly the same thing, but they can send these things at each other at a faster speed.
So we ran at 8 tera-electron volts. Now we're at 13 tera-electron volts. We're about 50% more energy for hitting the particles together.
Why don't you just go double it? Why don't you just go higher?
Because I don't think we're at that point where we can not only
That's the hard thing, is it?
Well, it's really hard. When you look at the technology it needs to just accelerate these things, we're pretty much creating the Big Bang in a test tube. It's not like you can just throw in more energy. And there's also containment of that energy. So what we're doing now is we're hitting them a little bit harder together in the hope that, number one, we can see maybe more types of Higgs boson. Maybe they have a different way, because if you hit it more, you get the particles breaking off for longer, so you can do more of an experiment because they degrade really quickly. And you might be able to get new particles off there that we've never seen before.
Okay, so, but you might not, because they might not be there, but we don't know until we do this.
We don't know, but we've been doing theoretical physics for so long. We have a lot of theories on what we will find, and, you know, this is where the experiment proves if it's true or not.
What might, just finally, what Is it possible that something will happen as a result of the Hadron Collider that changes our lives?
I reckon so, yes.
What might that be? Now we're getting to the nitty-gritty. What might that be?
Well, first of all, if we can find dark matter or understand more about the energy of how our universe is held together, that would be cool. If we can work out what dark matter is, we might have to figure out whether there are parallel universes, which would be even cooler.
That would be very cool.
And also little technologies like the radio wave, for example. It wasn't called the radio wave because we didn't have radios, but radios exist because of the radio wave, which everybody's listening to
So some other
now.
great thing might be.
So an amazing thing that we don't even know exists could be created.
So it could solve global warming. No, it could.
Well,
seriously, we don't need to worry about global warming anymore.
I think we need to worry a lot about global warming.
Because here's the thing. There's a parallel universe. That one is fine.
I think New Zealand should lead in the global warming research
too.
too.
I knew you would say that. All right, Michelle, it's always lovely to talk to you. Thank you very much, Michelle Dickinson.